All right, this is chapter 8. We're going to be talking about solutions and mixtures. You can see from the I can statements here some of the things that we'll be discussing in this unit. Different types of mixtures, solutions, colloids, suspensions. We'll be discussing the difference between electrolytes and non-electrolytes. I see a typo right there, that should say or. Predict whether a substance is soluble in water, which means, you have to know about the polarity of the substance. Predict the solubility at different temperatures, calculate concentration, be able to prepare a solution from a stock solution, a more concentrated solution, and then talk about colligative properties. And so let's just dive in. This will probably be a two-part recording. And so here we go. 8.1 mixtures. And so we know that matter itself can be divided into two main categories. The first category is a pure substance. And we've talked about these before. That includes elements, covalent compounds, and ionic compounds. But most of the substances that we talk about in nature are in fact mixtures. And mixtures contain two or more pure substances. And they can be further divided into two categories, the first being heterogeneous mixtures. And their characteristics is they do not have a uniform composition, or it could be homogeneous. So hopefully you've heard of these before. Concentrating on the prefixes hetero and homo, that helps you remember maybe the definition. And so hetero means different, homo means same. And so when we're talking about mixtures, we're talking about the composition itself. And so heterogeneous does not have a uniform composition, meaning it's not the same throughout, where a homogeneous mixture does have a uniform composition. And so maybe those prefixes will help you with the meaning of those words. First, let's look at homogeneous mixtures. And so a solution is an example of a homogeneous mixture. It contains very small particles. Usually the liquid solutions are transparent, meaning that you can see through them. And when you look at a homogeneous solution, you can't distinguish between the solute or the solvent. So the solute is the substance present in the lesser amount. This is the thing that is being dissolved. And the solvent is present in a greater amount, and it is what is doing the dissolving. And so an aqueous solution, you have water as the solvent. So water is typically referred to as a universal solvent. It does dissolve quite a few things. Not everything, but quite a few things. The next slide has some examples of solution. You may have not have thought of the air as being a solution, but it is actually a solution of gases. The most abundant being nitrogen gas, and of course there's oxygen gas and carbon dioxide and water vapor, along with some other types of gases. If you've ever been in the hospital or been around someone in the hospital, oftentimes they have an IV bag hanging of salt solution or saline solution, and that is a mixture of salt and water. Or if you've had any dental work done, perhaps you have some of the old style fillings that are silver, and that is actually a mixture we see here of mercury and silver. And so these are just three different examples of different types of solutions, containing very small particles, uniform throughout, and they're considered homogeneous mixtures. Next, we talk about a colloid. So a colloid is also a homogeneous mixture, but a colloid has larger particles, and they often have an opaque appearance, meaning you can't see through them easily. So think of like maybe fog or whole milk as an example of a colloid. The particles in a colloid cannot be filtered from its components. That's why it's considered a homogeneous mixture. And they never settle out. and they're always suspended. The second word here is suspension, and a suspension is actually a homogeneous mixture. It's a mixture that contains large particles that are suspended in a liquid. The particles are so large that they typically don't dissolve in the liquid, and after setting for some time or being placed in something called a centrifuge, which is a machine that spins around very fast, they can be separated into layers. And so suspensions typically form layers, where colloids do not form layers. This next slide is a video, and unfortunately the video did not work on my iPad, but you can go to the computer where you downloaded your notes, and this is an informative video about heterogeneous solutions, in particular some examples of those different types of solutions. And then we have this nice table here that kind of breaks down the colloids and suspensions and solutions based on their particle size. So we can see that the smallest particle size that has no settling and the components cannot be separated by filtration, these are called solutions. Next, we have a little bit larger size, anywhere from 1 nanometer to a micrometer. There is no settling, and the components cannot be separated by filtering, and this would be a colloid. And then finally, we see a suspension. For a suspension, we have the larger particles, larger than a micrometer. There is settling, meaning if it were left on its own, the larger particles would go to the bottom of the container. And because of this, excuse me, the solution can be filtered or can be separated with filtration. Excuse me. Or centrifugation, which is that spinning piece of equipment in the lab. Oftentimes when they're trying to separate blood, they use a centrifuge and they spin out the blood and separate it into its parts. All right, our next slide talks about electrolytes and non-electrolytes. And so when we refer to electrolytes, we are referring to a substance that conducts an electrical current in water. That is referred to as an electrolyte. Any substance that can conduct an electric current in water. And so typically those would be ionic compounds like sodium chloride. And when we put sodium chloride in water, this picture is showing you that there are sodium ions and chloride ions that have dissociated. That's the fancy word for dissolved, dissociates. They actually break apart into their individual ions, and because of this, they are able to conduct electricity in water. If a substance does not conduct an electrical current in water, of course it's called a non-electrolyte. And the example that they have here is hydrogen peroxide, H2O2. And you can see the difference here. These hydrogen peroxide particles, these brighter colored ones here, are not separating into ions. They are still held together with covalent bonds, and therefore they do not conduct electricity. This next slide is again a video that will not work on my iPad, but it is a very common test that is done in lab to determine whether a solution is an electrolytic solution or not. And so it's just interesting to see which of these solutions will actually make the light bulb light up. And you can see in this picture that it was only the ionic compound sodium chloride that was able to light the bulb. And so if you get a chance, go to your computer and watch this little video. It's informative for sure. So we can see that a strong electrolyte dissociates completely in water. So it breaks apart into its individual ions, and that is why it is able to complete the electrical circuit. Whereas a weak electrolyte dissociates only partially, if at all, leaving some uncharged molecules, and so therefore not good conductors. So in this table, you see some examples of strong electrolytes, and again, it's your ionic compounds, also your strong acids. We'll talk about those a little bit later on, strong bases. Weak electrolytes are listed here. Most of these are covalent compounds. Very few of these actually pull apart into ions, and therefore they do not conduct very well. And then you have these covalent compounds that do not separate at all, and so therefore they are not good conductors. The next term we want to look at is equivalent. And so an equivalent is a term that you will see, often abbreviated capital E, lowercase q. An equivalent is the number of moles of charge that a mole of ions contributes to a solution. The number of moles of charge. So the number of equivalents per mole of an ion equals the charge on that ion. So if I have a sodium ion that has a +1 charge, it's going to have 1 equivalent. 1 mole of sodium ions has 1 equivalent, as we see in this top row of our chart here. So in solutions that contains ions, there must be a balance between the total positive and total negative charge. And so that's, we can use this idea of equivalence to actually solve some problems. And so let's look at an example. It says if you have an intravenous aqueous sodium chloride solution and it contains 154 milliequivalents per liter of sodium ions, well, how many milliequivalents of sodium ions is a patient given in 800 milliliters of solution? And so we can use our equivalence as a conversion factor to help us solve this problem. So the first thing we want to do is to identify our known quantities. And so we can see from the prompt that we have 154 milliequivalents per liter, and that's of sodium ions. And we also can see that we have 800 milliliters of solution. So those are our known quantities. Well, what are they asking us to find? We want to know how many milliequivalents of sodium ion is the patient going to get. Okay, so once we've done that, next we want to think about our conversion factors. And so we're going to have 2 different conversion factors here because we need to be able to change from liter to milliliter. So we'll start with our equivalent. We know that we have 154 milliequivalents of sodium in 1 liter. Or we could reverse that. We could put 1 liter on top and 154 milliequivalents on the bottom. So here's 2 possibilities here. And then when we change from liters to milliliters, we have 2 choices here. We know that 1 liter is 1,000 milliliters, or we know that 1,000 milliliters is 1 liter. So there's our 2 options here. So we want to choose the ones to cancel liter and milliliter. So if we want to cancel liter and milliliter, we want to make sure and put those on the bottom so that our units cancel. All right, so let's see what we need to do. So we're going to start with our 800 milliliter sample. And so our first thing we want to do is change milliliter to liter. And so in order to cancel milliliter, we need that on the bottom. So we're going to choose the conversion factor that relates liters and milliliters. And we have milliliters on the bottom. So we can stop here and we can cancel units. And we can see that now if we stopped and did the math, we would be in liters. Let's take it one step further. We have our second equivalents that would change liters to milliequivalent. And so we know that for every 1 liter, we have 154 milliequivalent of our sodium ion. And so again, let's stop and cancel the units. When one unit is on top and the other unit is on the bottom of the fraction, they cancel each other out. And so now we have our unit that we're trying to solve for has been isolated, and we're ready just to do the math. And so this would be 800 divided by 1,000 times 154, and that's going to give us 123 milliequivalents of sodium ions in this 800 milliliter solution. And so this would be our final answer. So again, that's just another problem using the dimensional analysis that we've learned about previously. You can see that's a very useful tool to help you do conversions, changing one unit to another. All right, let's talk about solubility. So solubility is the amount of solute, remember that's the one in the lesser amount, that dissolves in a given amount of solvent. It's usually reported in units of grams per 100 milliliters. So keep that in mind, grams per 100 milliliters. So we have some different types of solutions based on solubility. If we have a saturated solution contains the maximum number of grams of solute that can dissolve. So think about a sponge. If you have a saturated sponge, it holds all the water that it can hold. If you put more water in it, it's just going to run out. So saturated means it can hold the maximum number of grams of solute, all it can hold. We could have an unsaturated solution, and that simply means that it contains less than the maximum amount, so it can hold more solute. Solubility can be summed up as like dissolves like. So let's talk about what that means. Most ionic and polar compounds, polar covalent compounds, are soluble in water, and that's because most of those are polar, and water is polar. And so like dissolves like. Water, being polar, can dissolve other polar molecules, but if you have a solute that is nonpolar, then you have to have a nonpolar solvent to make it dissolve. And so like dissolves like is the term that's used. Again, here's a short little video that explains solubility, so if you get a chance, take a look at that. When we have small neutral molecules with either oxygen or nitrogen or fluorine atoms, small neutral molecules with oxygen, nitrogen, or fluorine atoms that can hydrogen bond to water, these are always soluble molecules. So small neutral molecules with oxygen, nitrogen, or fluorine that can hydrogen bond to water are going to be soluble in water. Again, like dissolves like. If you have nonpolar compounds, they're only soluble in nonpolar solvents. You've heard before that oil and water do not mix. That's because oil is nonpolar and water is polar, so they do not mix. The example here, it says octane dissolves in carbon tetrachloride because they're both nonpolar liquids. They exhibit only London dispersion forces, so that's the only attraction between the molecules, and generally those are weak in nature, and so nonpolar compounds sometimes aren't very soluble. So when you are dissolving a solute in a solvent, This process is called solvation. So when solvation releases more energy than that required to separate the particles, then the overall process is exothermic. Exothermic. That means that heat is released. When the separation of particles requires more energy than is released, during solvation, then the process is endothermic. That's because heat is absorbed. So in solvation, you really have three different things going on. So first, if I were to dissolve, let's say, sodium chloride dissolved in water. I'm going to put that in some water. So first thing that has to happen is the sodium chloride has to break apart. So you have to break apart the sodium ions and the chloride ions, and that's going to require energy. You also have to break apart the water molecules. So one water molecule is attracted to another water molecule by intermolecular forces, so you have to break apart that attraction. And then when you put these together, then you're going to get salt and water. So you have a mixture of salt and water, and what happens is the water particles are going to surround the ions. So you have a ion water attraction, if you will. So again, this is an intermolecular attraction. So depending on which process, so basically you have three processes going on. You've got one, separating the sodium and the chloride, two, separating the water from water, and three, forming this attraction between the ions and the water. So depending on how much energy is involved, that determines whether the overall solvation process is endothermic or exothermic. When we speak of solubility, we have to look at solubility rules. So here are a few of those solubility rules that you will need as you work through the lab this week. We've already seen some of these as well. So you see here it says rule number 1, a compound is soluble if it contains one of the following. So anything from group 1A, any of the ions from group 1A, as well as of the ammonium ion, so NH4+. So if you have a compound with any of these group 1 cations or the ammonium cation, that compound will be soluble. Rule number 2 says a compound is soluble if it contains one of the following anions. So if you have an anion from group 17, the halogens, it's going to be soluble with everything, with some exceptions. The main exceptions are silver, mercury, and lead. So here we see also copper is one of the exceptions. So silver, mercury, or lead are what we refer to as the heavy metals. Silver, mercury, and lead. And so typically anything with these three, silver, mercury, and lead, are going to be insoluble. There's a few exceptions to that, but for the most part, those are insoluble. So a compound is always soluble if it contains nitrate, so that would be something to keep in mind. It's always soluble if it contains acetate, and acetate you may see written this way as well. It's kind of confusing because there's two ways to write it. And most things that contain sulfate are soluble except silver, mercury, and lead. And there's a few other possibilities here too. So be on the lookout for silver, mercury, and lead. And most of the time those are insoluble compounds. All right, let's take a look at how temperature affects solubility. So for most ionic and molecular solids, solubility generally increases as the temperature increases. And so if you've made some tea. Maybe you like to drink iced tea and you want to put sugar in it. Well, right after you make that tea, while it's still warm, if you put the sugar in right away, it's going to dissolve faster. Whereas if you put the tea in the refrigerator and it cools off and then you try to put sugar in it, it's much more difficult to get the sugar to dissolve. So for most things, solubility increases as the temperature increases. So by dissolving a solid in a solvent at high temperatures and then allowing it to cool slowly, you can achieve what's called a supersaturated solution. A supersaturated solution. You may have seen the candy called rock candy. A lot of times you'll see that the sugar is stuck to a popsicle stick or some kind of stick or string. That is formed by this idea of heating the water up to very high temperatures, adding more sugar than would normally dissolve, and then cooling it very slowly, and then these sugar crystals form. So that's called a supersaturated solution. It contains more than the predicted amount of solute at a given temperature. So as we said, for most things, the solubility increases as the temperature increases. However, for gases, the opposite is true. The solubility of a gas decreases with increasing temperature. So you see this at play if you, maybe you like to go fishing in the summertime. And the hotter it gets outside, the deeper you have to fish. So you have to, the fish, when in the springtime, when the water's cool, they're going to be up near the bank. But in the hot summertime, there's not as much oxygen dissolved in the hot water, so they have to go deeper in the lake where the water's cooler. And so solubility of gases, solubility of the oxygen gas that the fish are trying to breathe, decreases as the water gets hotter, so the fish go deeper. And so even in fishing, chemistry is at work. So now you learned something about fishing. All right, let's talk about how pressure affects solubility. So there's something called Henry's Law. Henry's Law says that the solubility of a gas in a liquid is proportional to the partial pressure of the gas above the liquid. And so the higher the pressure, the higher the solubility of the gas. And so this is at play in carbonated beverages. So when you have a closed can of, say, Pepsi Cola or Coca-Cola, whatever it is you like to drink, you know that can is under pressure, and you can hear that when you open the Coke can. You hear that pressure being released, and they do that so that they can get as much carbon dioxide dissolved in the Coke, so that it has a better taste to it. It's not flat. When you open the Coke can and you let it sit on the counter for a while, all the carbon dioxide comes out, and the Coke is not good to drink anymore. We say that the Coke is flat. Well, that just means that all the gas has escaped. So this video, again, on your computer, you can watch this video that explains Henry's Law. All right, there's a couple of calculations we can do with concentration. So the concentration of a solution tells us how much solute is dissolved in a given amount of solution. And so we can look at a weight volume percent concentration, and that simply is the number of grams of solute that has been dissolved in 100 milliliters of solution. And since it's a percent calculation, remember we talked about that percent of anything is part divided by whole times 100 to get it to that percentage. And so we see that happening here. We have the mass of the solute that's our part, divided by the volume of the entire solution, that's our whole, times 100. And so let's work through a quick example here. It says vinegar contains 5 grams of acetic acid into 100 milliliters of solution. So the weight per volume concentration is, and so you would just take 5 grams of acetic acid divided by 100 milliliters of my solution. So vinegar is nothing more than acetic acid dissolved in water times 100, and that's going to give me 5% weight per volume of acetic acid. And so when you buy a container of vinegar in the store, it contains 5% acetic acid. It even says so on the label. So take a look at that next time you buy some vinegar. We can also calculate volume per volume, percent composition. Same idea here. Part over a whole, part volume of the solute over volume of the solution. So if we have a bottle of rubbing alcohol that contains 70 milliliters of 2-propanol into 100 milliliter solution, well, the volume per volume percent concentration would be what? And so we take our 70 milliliters of our 2-propanol and we divide that by 100 milliliters of the rubbing alcohol, which again is just what you buy in the store in the bottle, and multiply that by 100, and it contains 70% volume per volume of 2-propanol. And again, that's what it says on the label, 70% 2-propanol. Another type of problem that you might see is using percent composition as a conversion factor. And so here's an example. We have a saline solution used in intravenous drips that contains 0.92% sodium chloride in water. How many grams of sodium chloride are contained in 250 milliliters of this solution? So we want to identify what we've been told. So we have 0.92% sodium chloride, and we have a 250 ml sample, and we're wanting to know grams of sodium chloride in this solution. And so we want to think about what do we know, what kind of conversion factors would we have. So we have 100 milliliters of our solution over 0.92 grams sodium chloride, or we could go the other direction, 0.92 grams of sodium chloride over 100 ml solution. And so we want to choose the conversion factor that is going to allow us to change from milliliters to grams. And so our given is that we have 250 milliliter solution. And we want to choose this second conversion factor because we have milliliters on the bottom. So 0.92 grams of sodium chloride. And we know that milliliters cancel, and that's going to lead us to grams. So we just need 2 figs here. So this solution contains 2.3 grams of sodium chloride. 2.3 grams. All right, another concept that is related to concentration is parts per million. So parts per million is abbreviated ppm. Sometimes you see parts per billion, which would be ppb. When a solution contains a very small concentration of solute, it's often expressed in parts per million. And so million is a number with 6 zeros, so that's why we have the times 10 to the 6th here. And so just be aware that parts per million are used quite a bit. All right, another word for concentration is molarity. Molarity is the number of moles of solute per liter of solution. And the abbreviation that we use for molarity is a capital M. Sometimes molarity is also indicated by using brackets around a compound. That also means molarity. And molarity, the equation here, moles of solute over liters of solution. And so we can use this to solve lots of different kinds of problems. The one we were given here, it says calculate the molarity of a solution made from 20 grams of sodium hydroxide in a 250 milliliter solution. So identifying our unknowns, we have 20 grams of sodium hydroxide and we have 250 milliliter solution. What are we trying to find? We're trying to find that molarity, which is, remember, mole over liter. So if we kind of keep these units in mind, that helps us set up our problem. So we're going to use the molar mass to convert grams of sodium hydroxide to moles of sodium hydroxide. That would be our first step. And so if we take our 20 grams of sodium hydroxide and convert that to moles. So in 1 mole of sodium hydroxide, there are 40 grams. And so gram cancels, and we are left with 0.5 mole of sodium hydroxide. All right, so we have the mole, and now we just need the liter. So we've got to convert our milliliters to liters. And so you can take 250 milliliters. We know that 1 liter is equal to 1,000 milliliters. And so we do some quick math, divide by 1,000, and that's 0.25 liters. Okay? And then we're ready to plug this into our molarity equation. Remember, molarity is mole over liter, and so we have what we need. So 0.5 mole over 0.25 liters is equal to 2.0 mole per liter, or you can simply just put a capital M. Capital M means molarity. Again, we can use molarity as a conversion factor, and we can solve even more problems. Conversion factor. And this conversion factor is going to relate moles of solute to the volume of the solution. And so to calculate moles of solute, we would simply rearrange the equation. And so here is our original equation over liter. And if we want mole, then we want to get mole by itself. And so we're simply going to divide both sides. I'm sorry, let me back up. If we want mole, we want to get rid of liters. And so liters is on the bottom, so we're actually going to multiply both sides by liters. And so here, the liters would cancel, and we would be left with a new equation that would say mole is equal to molarity times your volume in liters. And so that is how you would rearrange if you were solving for moles. On the other hand, if we wanted to calculate volume, we want to get liter by itself. So since liter is on the bottom of the fraction, that's going to take a little bit more work. So we would start by multiplying both sides by liter. And again, that's going to cancel the liter here. And then we want to get rid of molarity, so we want to divide both sides by molarity. And so that cancels the m's here. And so you're left with a new equation after all of that. And that says liter, which is your volume, is equal to mole over molarity. So that's a helpful thing to be able to rearrange the equation to solve for either moles or volume. All right, our example here, it wants to know the volume. What volume in milliliters is a 0.30 molar solution of glucose that contains 0.025 moles of glucose? So we want to identify what we're given. So we have a 0.30 molar solution of glucose, and we have 0.025 moles of that solution, and we're wanting to find the volume, and they want that volume to be in milliliters, so that'll take an extra step. Okay, and so we want to have our new equation, so let me rearrange that again for you. We're solving for liters. And so since liters is in the denominator on one side and we need it on the other side of the equal sign, here's a quick little tip. We can simply, we saw the math a minute ago and you can go back and review that, but you can simply just switch places with those two and you will have your new equation, mole over molarity. So again, if you need to go back up and see that math, why that's possible, feel free to do that. And so once we have our new equation, we can simply plug in the numbers. And so if we want liters, we're going to take our 0.25 moles whoops, 0.025, don't forget that, moles divided by the molarity, which was 0.30 molar. And maybe it would be best to mole per liter, and that way you can see that the moles actually cancel and liter is left, and that's going to give us 0.083 liters. And then our last step would be to convert our liters to milliliters. So don't forget that 1,000 milliliters are in 1 liter. Set it up so the units cancel and we end up with 83 milliliters of our solution. All right, I think this is a good place to stop our video, and we will pick up in our second video with 8.7.